Okay, today we will begin with an overview of the topic first, right? Then, depending on the time remaining, we can spend some time doing some questions and for you to clarify if you have already done the MCQs. Okay, I'm not looking at the chat, so if you have any issue, just pick up. Okay, I'll be going through this topic, right? Not as a first encounter, but more like a going through of key concepts, presuming that you have already learned this partially in school, and also, right, the problem solving technique, okay, how different concept, right, lends itself to different kind of questions. Okay, so let's begin. First thing that we learn in this topic, right, is the Newton's law of gravitation, which states that the force of attraction, right. You see, for Newton's law of attraction, right, there are two ways of writing it. You can say, right, it's two particles. Okay, particles, right, key thing is not that it's small mass. Okay, other, right, is point masses. Yeah, so they are meant to be concentrated at the point. Okay, but in real world, we always have the significant size, right? There's dimension to things. So we'll talk about how we may modify the later on. It's proportional to this one, right? You must memorize because it will always come out. Okay, and more likely to come out for your block test now compared to promo. Just promo, you'll be tested on more things already. Gravitational potential. For block test, right, you'll be only the first half. I presume okay. Maybe EJ will test more. I think Hua Chong will only test until the first half. The product, okay, the masses inversely proportional to square of separation. So if this is not point, so you see for point mass, right, it's just one dot and one dot, right? So the separation is very easy to conceive. It's just, right, one dot to the next dot, right? However, right, if you are talking about normal planets, right, clearly, right, you have to consider their center of mass. So if you are talking about bodies in general, okay, so this one doesn't mean that they will be point particles. Then, right, it will be square of separation between center of mass. So this is the extra part that you need to write if you choose to write two bodies rather than two particles. Okay, so normally, right, we'll write the formula, the gravitational force as Fg, okay, subscript G, so G mm R square. R, right, we also want to be quite clear. Sometimes, right, we'll see capital R, sometimes we'll see small r. Usually, right, small r is for separation, okay, and capital R, right, are for maybe radius of some well-known things. For example, radius of a certain orbit or radius of the planet. Okay, so you'll see a lot of subscript in this topic. Okay, because, right, you will have mass of a planet, mass of a sun, etc. Next up, right, is the idea of gravitational field. When a man, right, stands on Earth, okay, clearly, right, Earth will experience the same gravitational pull as the man. Okay, yeah, it's mutual, right? By Newton's third law. However, right, the acceleration is going to be a lot different. The acceleration on man, right, is Fg divided by mass of the man, which is like 60 kg. Whereas, right, acceleration of Earth due to man's pulling it, okay, same force but divided by a huge mass. So this is 6 times 10 to the power of 24. Okay, so there's a 10 to the power of 23 order of difference, right? Okay, that is huge. Yeah, that's huge difference. So it seems to suggest, right, that actually, although the force are equal, but then, right, it's equal because the force is the product of our masses. Okay, but who is giving more? Okay, in this, seems that the Earth is actually the main thing that contributes to the force, right? Not the man. Okay, so we can think about the contribution, or rather, right, the attractive power, right, of Earth being actually more dominant. Okay, so thereby, right, this breeds an idea of field strength. So field strength, right, we do not want to just know what is the force. We want to know, right, what is the normalized version of the force. Just like here, right, you see the attraction due to Earth on the man, right, sort of as a particular acceleration. Okay, so what if, right, we change that away, okay? We think about this, right, as the attractiveness of Earth, okay? And we think about this as the attractiveness of the man. So essentially, right, we want to come up with a normalized version of the attractiveness. So you discount away, or it's still a attractiveness, so it's a force, but it's a force that is discounted by the object that you are attracting. That means, right, for Earth attracting man, you discount away the mass of the man. Man attracting Earth, discount away mass of the. Another way of seeing things, right, is that, let's say at a certain distance, okay, away from Earth, then you have two objects, okay, this one and this one. So maybe this is 1 kg, this is 3 kg. Maybe, right, the weight is for here is F, okay, for this guy is 3F. But, right, if you discount away their masses, right, at this location, okay, F divided by 1 kg, you get a certain value, okay. F divided by 3 kg, you get the same value, the idea of G, okay. So in general, G is simply equals to G divided by the discounted by the mass that you are attracting, okay. So this is the more general formula, okay. So in general, right, what is gravitational field strength? So gravitational field strength, gravitational force, okay, on a small test mass. So in general, right, in the universe, there's always a lot of planets, okay. So for example, you have a Earth here and you have a moon here, okay. You have no idea, right, what is the field like, because now you have multiple planets, right, exerting a pull, okay, yeah, in this region. How do you know what is the field like, okay? So you simply, right, go to a certain point, you put a small test mass, okay, this M. So maybe, right, at this location, it turns out that, oh, this guy, right, experiences a force this way, okay. And you can also do it many times, at this location, right, maybe this guy experienced a force around this way, okay. That is to allow us, right, you see, you put a small test mass there, then you figure out the force already, divide it by the mass, okay. So at those two locations, okay, turns out, right, that this is which is the force divided by the, that's the idea, okay. So field, right, is a property of, field strength is a property of a point that is within the vicinity of bodies, right, capable of generating due to single body, okay, the G due to a single body. What would it be like? Suppose you only have one planet, okay, this mass M, then you put a small test mass here, so it's small m, right? So you know the force is definitely this way. So the G at this point, right, is equals to Fg divided by mass, okay? So it's Gm m over r square over m. Due to a single body, right, then this is your Gm over r square. And this arises from the Newton's law of gravitation. So Gm over r square, then divided by the m. So in general, right, you see, this form is most generic, okay. This is the most generic, yeah. So this version is specific, it's only for the context of G due to a single body. Then what about, right, if we have a few body, don't say too many, let's talk about just two, okay. Back to the Earth and Moon case, right, how do we calculate and find out the G at various known distances, okay. So we could go to, let's say, this point here, okay. This point here, right, by the formula Gm over r square, so it's very near Earth, right, and very far from Moon. And mass of Earth is like much greater than mass of Moon. Therefore, right, at this point, you expect that this is the G due to Earth, okay, and it's going to be large compared to G due to Moon, which is small. And you can actually use the formula to figure out the value of these two arrows, okay. So you do a simple vector sum to find out what's the resultant. Okay. Similarly, right, when you are nearer to Moon, okay, let's say this point here, you expect the G due to Moon is going to be much larger, okay, compared to the G due to Earth. Yeah, and that's how you calculate, okay. And usually we're not interested in all these random points. We're interested in one particular point, right, whereby the size of both arrows, right, are the same, okay. Size of both arrows are the same. So that means, right, these two being vectors, right, they will cancel each other out, okay. So turns out here G is 0. This point, right, we call it neutral point. Neutral point. What is happening at neutral point? Because G is 0, we also call this, right, this phenomenon true weightlessness. So how to figure out what is the location? So suppose, right, you call this distance x, okay, and maybe you already know the distance from Earth to Moon, okay. So this is r. for example, then you can go on and calculate lah. So what is the value of x? So it's GE equals to GM mass of Earth over x squared. The G, capital G, right, we cancel out lah. I'll just write it, okay? Mass of Moon over R minus X thing square, okay? And go on and solve, can? That's how you find the location. Okay, any question up to this point?
Wait, so it's like the G, right? Is it also like the acceleration that it will experience, like a point mass will experience at that, if it was placed at that like area?
Yeah, exactly, okay? Exactly. Because, right, it happens that A is equals to net force over M, okay? Therefore, the A is also equals to the G, yeah? Because the net force happens to be the gravitational force divided by M, so A is also equal to G, same. There's actually a name for this phenomenon. I mean, it's actually quite coincidental, because both Newton's second law, net force equals to MA, and gravitational force equals to mg. This causes, right, this coincidence causes the A to be equals to G. Okay? The name of the coincidence, right, is equivalence principle. You don't even know, it's just for fun. Okay. Let's do a simple example, okay, on this. Suppose, right, we have a Earth Moon system. Okay, let me draw it again. Earth Moon system, and we know, right, the neutral point is, let's say, here. Okay, sorry. Neutral point is somewhere here, closer to Moon. You know quickly, right, where's the neutral point? You simply, right, use the idea that the force, the pull, right, gravitational pull must be equal, right, at the neutral point. A massive one must give a handicap to the less massive one, or massive one stand further away. Now they are playing a tug of war. Suppose, right, now suddenly we have a sun, okay, because obviously the sun is nearby as well. Okay, not so nearby, but it's massive. Okay, where do you think, right, the new neutral point will be if you consider just Earth and Moon? But if you throw in the sun, okay, where do you think this new point will be? So original point, right, must be lying along this line, right? Okay, where do you think the new neutral point will be? Let me review lah, okay? It's just be shifted by a little bit long. So it may be shifted by a little bit more. So let me erase the original one. Basically, right, the idea here is if you have 3, then you just have to balance 3 arrows, okay? So the net, right, at this point is still 0. So here you have 1 arrow due to Earth. Here you have a second arrow due to Moon, okay? Yeah. And then there, right, you have a third arrow due to such that, right, these 3 arrows add up to give you 0, okay? Yeah. So it'll be something like this. So when you deal with field, right, okay, you must be very mindful you're always dealing with vectors, okay? Questions like this, right, no need calculation one. Once it's got 3 points, just the calculation will be very messy. So usually this will come out as an MCQ question. They will just put various points for you to choose. Where's the neutral point, okay? So it's just to test you, right, whether you can see how the vectors, right, must be like. So they may give you a few options, right, like this is option A. This point, the correct one is option B, or maybe they give you another point here, option C, another point here, option D, something like that, okay? Just give you some things for you to choose. So it is definitely not A, because, right, Sun is to the right of the Earth-Moon system, okay? So A will be the original neutral point for just Earth-Moon. But when Sun is there, the new neutral point must shift, so that both vectors, right, now have a leftward component to balance the rightward component towards the Sun, okay? Moreover, right, it cannot be C, because C will be too near Earth, so the attraction due to Earth will be much stronger than due to Moon. So the Y direction, right, according to our diagram, cannot match. Cannot be D, because, right, Sun's mass is a lot larger, okay? So if you put in the center of this setup, right, then you'll be far from both Earth and Moon, and relatively, right, okay, close to Sun, and Sun will dominate, okay? Yeah, the Sun's mass is way bigger. So the neutral point, right, must skew all the way, right, towards Earth-Moon side compared to Sun. Understand? So this is just a qualitative question. Let me go back one step. I forgot to discuss this idea. Not very important, right, but still quite useful. Actually, I shouldn't say that. Let's try to draw, right, few lines due to a single body, okay? Let's say Earth. This is how we draw few lines, field lines, right, are always, right, perpendicular to the surface of the planet, okay? So you can just draw like perhaps 8 lines, okay, like orthogonal shape. And you can see, right, that the lines, right, will be closer to each other, okay, in certain region. Let me read the arrow first. Number one thing, right, is the lines, right, are closer to each other in this region, and further this region, okay. So where field lines are close, right, this means that field is strong. Field lines are far, that means the field is weak. That's how field lines, right, show you the strength of the field. Okay, this is exactly like magnetic field. You draw and you saw magnetic field diagrams a lot of times already, since secondary school. But gravitation is the first time. You always know that there's gravity, but you haven't drawn gravitational field lines before. Okay, so this is how we interpret field. Later on, we'll talk about how field and gravitational potential link. Okay, but that will be the next time. Now, right, let's zoom in. Okay, suppose, right, you zoom in onto this region. Okay, let's say the near the North Pole. Okay, so you zoom in near the North Pole. It doesn't matter where lah. All I'm trying to say is we zoom in. Okay, so we see a lesser part of the Earth, right? So how will the field lines be like? They'll always be perpendicular to the surface, okay, for a spherical body. So the field lines, right, will be like that, okay. You can draw a few more lines. And if you zoom in further, then, right, you'll see that your Earth, right, will have been almost flat, okay. And then you can see, right, that the field are hence, right, going to be just parallel to each other, okay. It's just a result of you zooming in, yeah. Since, right, we have said that when lines are far and when lines are near, it means different field. Here, right, we can see the lines are all equally spaced, yeah, equally spaced. They are all same direction, okay. And so this actually means, right, that the field is actually uniform. Where is G field treated to be uniform? It is when it is near Earth's surface or near surface of any planet in general. So that's why, right, near Earth, like how near? A few km, is all considered near Earth. So gravitational field is almost uniform. It's just a 9.81. This is representation of field. Let's go on to a application. Okay, one of the very important application of gravitational field is, we missed out something. Okay, let's relate, right, field to things. Field versus, right, the density. Okay, field versus density, right, you see on the surface of a planet, okay, yeah, surface of a G, right, okay, this G is equals to Gm over the R, right, we change it to capital R, which is the radius of planet. Okay, so this is right at the surface. Then we can see, right, m is the mass of the planet. Convert it into in terms of density and radius. We have a G 4/3 R cubed times density. Okay, then over a R square. And you can see, right, that the R cubed and the R square will cancel out, leaving 4/3 G. This is a constant. It's just a constant. Then you're still left with a R and you're still left with a. So this tells you, right, G on the surface. Okay, I better write a subscript in case, right, you treat it too broadly. It's simply, right, proportional to R and, okay, you see a lot of MCQ questions, right, of this type one, testing your ability, right, to predict the G. They'll give you planet 1, this density, this radius. Planet 2, 1/3 the radius, twice as dense. What is the G? Okay, so you use this relationship to figure out. See, in doing so, right, we actually have made a few assumptions. Assume, right, number one, planet, right, is a perfect sphere. That explains the 4/3 pi r cubed. So the assumptions are perfect sphere. Moreover, right, we are also assuming that the density is the same. So it is a even distribution, okay, even mass distribution. Why we say that these are assumptions, right? Because in reality, G, okay, from being number one, right, it's like for example, you have, like, let's say the Earth, right, instead of being a perfect sphere, maybe this instead. Of course, it's not so exaggerated, but it's actually somewhat true because, right, for Earth, you actually have most of it as the ocean, right, or seawater. So when Earth is spinning about its own axis, right, water near the equator, which also, right, where Moon is sitting, okay, Moon is sitting on the equatorial plane. Therefore, right, water near equator, near Moon, get attracted towards Moon. So the equator bulge. On the opposite far side, right, okay, Moon's gravitational attraction is weaker. So water also bulge, okay, because, right, there's no less attraction to pull the water there, okay. So where's Moon? Moon is actually here. Here, right, this extra bit of water appear because of stronger attraction. Here, extra bit of water exists is because the lack of attraction. Yeah, that's why it is allowed to be further away. So the real Earth is actually, right, non-uniform in terms of the shape, or rather, it's not a perfect sphere. Moreover, right, real Earth also have different substance underground. Okay, it's also different substance. Okay, and you may see a question, right, like this in your school tutorial. So they will say, oh, for example, right, G everywhere is a certain value. Okay, G everywhere is a certain value. Then under the ground, right, maybe you're standing on top of Saudi Arabia or the Persian Gulf area. Then you say, hey, wow, the G here, right, is like smaller. Okay, this is the G here. The G here is smaller than normal. So what is the G? What causes the difference? It's because, right, instead of having mineral earth, okay, underground, which is quite dense, right? Okay, let's say you have iron or sand or whatever, right? Or it's quite dense. But if underground you have oil, and the oil, right, their mass is mass of an equivalent chunk of oil, right, is lesser than that of rock. Therefore, the G contribute, right, is lesser. Therefore, when you're standing on top of an oil deposit, okay, you're doing some oil exploration. When you see the G drop, you know must be something different underground. Okay, so these are some of the factors. So questions in exam, they will ask you also state the assumption or it could be a question on oil exploration and you have to explain why the G is lesser or G is more and what does it mean. Okay, let's go on. Let's talk about the most common application of circular motion, of gravitation, which is, right, circular motion. We have a planet Earth here, okay, and say, right, we have a satellite. This satellite is going in a circle around Earth. Okay, what that allows it to go in a circular motion, right, is there's a gravitational force. Okay, I must have a gravitational force so that it can go in circle, because, right, once to go in circle, must have centripetal force. So here, right, the role of gravity in allowing things to go in circular orbits, right, providing for centripetal force. Okay, please write in full. Okay, I'm just taking a shortcut here. Okay, these two must write in full. Gravitational force provides for centripetal force. So happens, right, that, okay, for this particular V, this particular radius, this radius here is also the separation between the two bodies, right? So happens, right, that you have GMM over R square. Okay, so this R is talking about separation. It's equals to MAC. So MAC got two forms. So let's just do each of the form. And here, right, the R, we are talking about radius. Okay, circular motion. We're talking about radius of circular motion, not separation. Okay, in this case, they happen to be the same. Later on, we'll see one case is different. So let's solve for the first version first. So you have your GM over R, right? You can bring over, combine on the same side. So you have R cubed equals to 4 pi square, 2 pi over T. So 4 pi square over T square. From here, right, you can flip the both sides around. So you'll see, right, that the T square is actually equals to 4 pi square over GM times R cubed. So this is the famous T square proportional to R cubed. So the larger the orbit, the larger the period. Okay. Therefore, right, Earth compared to Mars, which one have a longer year? Which one have a longer planet year? Do you know what is the year or not? What's the significance of year with respect to Earth's motion around Sun? A year, right, is the period of the planet. So Earth is closer to Sun compared to Mars. Mars is further. So 1 Earth year is actually, right, shorter than 1 mass years. 1 mass year is around 580 something day, if I'm not wrong. I forgot already. Okay, let's continue. On the others, you use the other form of the equation, right? Then you have a Gm over R, right? Also bring over. So here left with a R. So here you have a V square. Okay, so this form is more straightforward. V is simply proportional to 1 over square root. So the smaller the radius, the faster the speed. And actually, right, here we KIV, but we don't talk about too much about it also first, okay? That's right. If we don't cancel out the small m, we leave it, right? From here, you can have another one, which is, right, half m v squared, because you have mv squared over r, right, will be equals to gmm over, if your school have taught gravitation fully already, right, you will have known this by now. Okay, so K is actually GMM over 2R. So these are the key things that we need to know. All circular motion problem, right, for in this topic, okay, you're all involved this kind of procedure. You either equate the FG to MR omega square or MV square over R to try to solve for something. What else do I want to say here? Okay, more. Okay, let's look at a second type of circular motion. Okay, the second type of circular motion, right, is a bit more different. So you have, right, the first type applies for a small body orbiting about a much more massive body. For example, satellite around Earth. Okay, Earth around Sun. But what if, right, you have two bodies which are quite similar in terms of masses? Okay, let's say this is two stars. This is also what we call binary star system. Basically, right, these two are two stars, okay, and you have this as, let's say, 3m, okay, and this as m. You see, it's actually comparable in terms of size. So what kind of circular motion, right, they tend to perform? They will tend to perform, right, this motion whereby this is the center of mass. I'll talk about it in a while. This guy, right, will orbit about this center of mass this way. The other guy, right, will orbit about the center of mass, right, that way. Okay, this is the line connecting their masses. Okay, so this is the center of mass. So it turns out, right, that when you have this kind of binary star setup, they will both orbit about their center of mass. The center of mass don't move one. It's a fixed point. Okay, but they will orbit about this point as though, right, they are like two fishballs stuck on a satay stick. Okay, which is massless. Okay, two fishballs got mass, satay stick no mass, and right, you pivot the system, right, at a particular point that it somehow can spin about. Okay, so it's like a satay stick, right? The whole satay stick system spin, which means, right, intuitively they must have the same omega and the same period, because they must clear one circle in the same time, because they are part of a connected system. Ask ourselves, okay, how do we know where is the location of the center of mass? Center of mass location, right? You can use this satay stick analogy, okay? And in a normal satay stick, right, suppose we have these two fishballs attached, and we want to put this on a, let me redraw, okay? This is a fishball. So these are not planet yet, these are just fishball. And then, right, I want to pivot it such that it will stay balanced. I know, right, that I must pivot it such that this is a D1, this is a D2, this is a M1G, this is a M2G, right? So I will want to have a M1G times D1 equals to M2G times D2, okay? So that is how we balance a satay stick system on Earth, right? If this is not satay stick system and this is not on Earth clearly, these are two giant stars. And right, we have a similar equation as well. Or instead of looking at this weight, instead of having a fulcrum, okay, you simply, right, just delete away the G. This will tell you the location just as well. Okay, so it's simply, right, M1D1 equals M2D2. You can think of this as a moment of mass. Okay, moment of a mass. So it's just mass times distance equal mass times distance. Normally we use moment of force, right, which is force times distance, but now it's mass times distance. Okay, this allows you to find where is it. Therefore, right, for this setup, if I call this distance, right, this one is R, okay, to the center of mass, let's say X. Very clear, right, that this X must have been 1/4 of R, okay. If x is 1/4, then the remaining r minus x will be 3/4. Therefore, 1. Let's go on and use this set of numbers, right, to solve. So we know this x already. R upon 4, 3r upon 4. Okay. What is causing them to go in circular motion? It must have been the force of attraction between them. Okay. This is the Fg. This is also the Fg, and they are equal. Newton's third law. So let's consider, right, the 3m guy. For the 3m guy, right, forces causes, so it's still Fg provides Fc, right? But now, right, the equation will look a little bit different. Okay. So we have Gm times 3m, okay, r square. Okay. Here, right, this is the separation, and this equals to 3m. You see, mr omega square, the first m is which mass are you? We are talking about 3m. What's the radius? R upon 4. And let's imagine, right, let's pretend that we don't know that they should have the same omega. So I'll call this omega 1. This is our equation 1. Then let's look at m, right? You have the same thing. And I don't want to rewrite the equation, the Fg provide Fc already. Let's go straight. So you have Gm times m over r square. Still the same. Okay. Our right hand side, right, is different. So you have m 3r upon 4 omega 2. So we are pretending that they have different omega, or rather, right, we don't know. So if you don't know, you cannot assume them to be the same. So that's why I label it as omega 1 and omega 2. So you inspect both equations, right? Okay. You realize, right, that left hand side is the same. Left hand side is the same because Newton's third law, Fg must be the same, actually, right? Then you look at the right hand side. Here you have a 3mr upon 4. Here you also have a 3mr upon 4. Turns out, right, that left hand side, right hand side, all the same. In fact, right hand side, right, the coefficient to the omega is the same, which means, right, omega 1 must be equals to omega 2. T1 must be equals to T2. It's only one period. So whenever you want to find the period of the binary star system, you just need to solve equation once. Okay, don't need to solve it 2 times because they will give you the same conclusion. Okay, but of course, right, they have different V. Any question up to this point? Okay, next, talk back about the no. I don't want to talk about that first. Let's go back to things which are on Earth's surface. Okay, things which are on Earth's surface. We know, right, that Earth actually rotates about a particular axis. That axis, right, is almost, right, our North Pole to South Pole. It's actually off by a little bit. For convenience, right, we will not distinguish. So we just call this, we just say that the axis passes through the poles. Okay, this rotation, right, which way? Okay. For example, right, if you have the sun here, okay, every day you will see the sun, right? That event is called sunrise. Earth's rotation, right, must have been like this. Why? Because, right, people, actually I should draw the sun on in another perspective. Let's say, right, sun is somewhere here instead. We are viewing, right, in like a 3D way. We draw it further. Sun is like somewhere here. You're looking at the sun, right? So who will get to see the sun first? Is people who are looking in the eastward direction will get to see the sun first. So it must be, right, people here. So that implies, right, that the rotation is this way from west to south. West to east. Okay, yeah, because people at the east see sun first. And what are the consequences of this rotation? Let's draw this Earth bigger and draw objects, right, on Earth. You could be at various parts. Okay, let's say it's here on this one case, this another case, and this is a third case. So let's consider, right, these 3 cases. The simplest case, right, here is actually, right, the guy that's standing on the axis, okay, which is the North Pole guy. Because, right, for the North Pole guy, things are simple. There's a weight of this equals to, in fact, all 3 have lah. Okay, let's just draw it in first. All 3 have Fg. Okay, and because, right, it's at the North Pole, so his motion, right, due to Earth rotation is simply, right, if you are alien looking from far away, this guy is just doing a ballerina turn, or he's just, right, spinning on the spot. He never moved. Center of mass actually never moved. Is he performing any circular motion as a result of Earth rotation, which means, right, net force on him must be 0. Okay, so this is your normal contact force and is equals to, okay, this guy's case is so straightforward. What about this guy on equator, right? He performs a huge circular motion, and you can see, right, the radius of this circular motion is the radius of Earth. Therefore, right, there must be a net force on him. So that means, right, normal contact force cannot be equals to mg. It has to be smaller. Okay, such that, right, at this location, we'll have, right, Fg minus n equals to mr omega square. So let's go on and find, right, what is the value of the n. Okay, so we have, right, here Fg I write is mg. So we have, right, n is equals to g minus r omega square. Let me tell you the r. R is actually equals to 6.4 times 10 to the power of 6 meter. Okay, omega, right, is 2 pi divided by 1 day is 24 hours. So this is 864. Calculate what is the r omega square. Press calculator. I want you to try and feel for this number. I hope you tried. So your g, right, is your 9.81. Okay, this r omega square, right, turns out to be something like 0.0, okay, around there. So this means, right, that normal contact force, right, that a object, right, on Earth's surface at the equator experiences, right, is only equals to m times 9.78. Okay, so it's lesser than mg. But is it very significant? Not quite lah. Okay, it's just a little bit lesser. So this brings us, right, to another point, which is, right, if we were to, let me shift this away. If we were to distinguish, right, two contribution, okay. So see, this n is for an object that's on surface, right. So what if you have an object that's on equator, yeah, near a surface, but it's falling. Okay, so what is the g that he will fall with? G that this guy will fall with, right, here, g of free fall, or I should say acceleration of free fall. As a result of part of the g needed to fulfill centripetal acceleration, right, then this acceleration of free fall is actually, right, the g minus away acceleration of centripetal, minus away centripetal acceleration. Okay, it's trying to say, right, g is actually 9.81, but part of it, right, needs to contribute centripetal acceleration. The remaining, right, will be used for causing it to accelerate, okay, and gain speed. So this is your 9.78 meter, this is your 9.81, this is your 0.03. So things, right, that are undergoing free fall near equator of the g need to provide for centripetal force, okay. Therefore, it wouldn't be free falling at 9.81. What about the guy, right, who is at some other, and right, this one is what you have done in circular motion already, okay? So you just have to deal with the questions may ask, right, what is the omega of this guy? So it's more like a circular motion problem. You need to solve for forces, right? Usually, not really. Okay, you got to realize, right, that here things get a little bit weird. This one you don't need to be too bothered. Okay, so you see, this is your Fg, right, which is towards the center of Earth. In the end, you need to have a centripetal force, net force towards the center of this guy's rotation, right, somewhere here. That means, right, your normal contact force, your contact force cannot be just normal. You'll be slanted by a little bit. Okay, yeah, such that, right, you have a slanted normal contact force, and you have a Fg, and this is your, this position, right, analysis is not very important. So the key, right, is distinguish between North Pole and equator. As a result of Earth's rotation, right, okay, then, right, your satellite, right, will get interesting, okay, because, right, you want to have a satellite, okay, that always appear above a certain point on Earth. Okay, that means, right, if you look from the North Pole, this is the Earth. Earth is rotating about its axis, right, which is here. Okay, so this is the Earth's rotation. And if you want to have a satellite, right, which is orbiting always, right, above Earth's surface at the same point, right, how must this satellite be? Okay, firstly, right, this satellite, so meaning, right, when you are here, okay, you see the satellite here. A while later, right, maybe half a cycle later, a quarter of the day later, you become here. You see the satellite. Sorry, you see the satellite here. Later on, you see a satellite here. Later on, you see a satellite here. The satellite is always, right above you. So this brings, right, the first characteristic of this satellite. Okay, the period, right, that rotation about its axis. I.e., right, for Earth is 24 hours. But questions, right, sometimes may give you other planet. So you just have to adjust. Number two, right, in order for this also to take place, same direction, okay, as Earth's rotation. This is also very straightforward. Number three is less obvious already, okay. This satellite, right, must be a bit of satellite must be on equatorial plane. And when these three conditions are fulfilled, right, okay, we have a geostationary satellite, okay. Geo means, right, Earth. Stationary means with respect to, stationary with respect to Earth. Let's elaborate on the third point. You see, where is your equatorial plane? Let's look at Earth right now from another angle. So this is the equatorial plane, of this equator. The rotation is about here. So, right, you see, gravitational force must be pointing towards center of Earth. So the gravitational force must be pointing this way. Therefore, right, the center of the motion has to be center of Earth as well, okay, for this satellite. Satellite's motion, right, has to be in equatorial plane in order, right, for it to be always, right, above the same point. You can use counter examples, right, to convince yourself, right, why it must be so and not other things. So, for example, what if it's not? If it's not, right, okay, such as this, it's not on the equatorial plane, then what will you see? For the same guy on the Earth surface, right, half the day, okay, let's say it's also 24-hour orbit, right? Half the day, you'll see that the satellites in the north side of the sky. Half the day, you'll see the satellites south side of the sky, because, right, it is not on equatorial plane. It wouldn't be on the same spot on the sky. In order to be same spot, it must be equatorial plane. Then can. There are other types of purpose for other orbits, but geostationary satellite is the most obvious one. This is the one that's always tested, and we need to be able to deal with it fluently. So with this, right, how do we find the radius, for example? Okay, so you have a FG provides C. This is always, right, the first statement, okay, for all this orbit problem solving. So you have GMM over R square. You see, which form of the equation do we want to use? This being geostationary, you have 24-hour period. Therefore, we want to use MR omega square, because we know the period. So you have, right, T square is equals to, we want to solve for R. I forgot. R cube is actually equals to T square 4 pi GM over 4 pi square. Okay. Can you try sub in the values for mass of Earth 6 times 10 to the power of 24, sub in period, and find what is this R. Okay, maybe give you 2 minutes. Okay, if you have calculated correctly, right, you're supposed to get something like R is equals to 4.2, or it could be 4.3, I forgot already. Maybe it's 4.3 times 10 to the power of 7 meter. Okay, I can assure you, right, that many of you will have difficulty, right, getting the answer despite knowing all the terms, okay, because, right, it's just hard to press in calculator. Often, right, we make mistake, okay. So let me teach you a method to calculate, right, this kind of things, right, without error, okay. So you always, right, deal with the number, okay. So in our calculator, right, what will we do? We'll take a 6.67 times 6.64 square, then divide by 4 pi square. Okay, you don't go and punch in the power first. So this is the number part. It's the number part. And the power part, right? So you have what? You simply have minus 11 plus 24 plus 8. So you have 21. Here is how much? I don't know. But so that way, right, you don't have a lot of 10 to the power of something to key in. Okay, you treat the power separately, then you combine together. So, and let me just try to get a number to write down here. Okay, so here, right, is actually 75.7. Okay, and this one you have a 10 to the power of 21. Okay, so you want to root this number, then very, very easy. What? Okay, let me just take a look what else have I not covered. Okay, I think I generally cover everything I want to say for today already. Okay, the second half will be on gravitational potential. We